Okay, so this is my outline, and I think in the first video I'll talk about the first two bullet points, so mean curvature flow and brachyflow, which is a generalization of mean curvature flow to singular sets. And then I'll talk about the case of rotational symmetry for smooth self-expanders. And the second video I'll do the rest of the talk, which is to make sense of rotational symmetry for more general brachyflows and give an outline of proofs. Okay, so say a family of embedded hypersurfaces sigma t satisfies the mean curvature flow if the position vector x moves in a normal direction with velocity equal to the mean curvature vector. So this is a very well-studied, extensively studied extrinsic geometric flow, and it's perhaps the first, or perhaps after the curved Schrödinger flow, so the second examples that we usually give for geometric flows, and there being a plethora of works in different directions on curved flows, and here are some examples. So the trivial examples or the static examples are the minimal surfaces. They remain the same under the curvature flow. These include, for example, the hyperplanes, the catenoids, the helicoids, and if you're familiar with minimal surface, there are also a lot of them. So that's the first moving examples are the shrinking spheres. So the sphere of radius r in Rn plus 1 has mean curvature n over r, so sigma t equals the sphere radius square root of minus 2nt with t in negative infinity to 0 is a smooth solution to the mean curvature flow. So the flow obviously it's called shrinking sphere, so you can imagine the sphere, right? The radius gets smaller and smaller as t goes larger, and eventually shrinks to a point. Okay, so that's the first non-trivial, moving example of a mean curvature flow. And more generally, we'll have the shrinking cylinder, so we can cross the sphere by a Euclidean factor, which does not affect the sorry, I forgot the radius here, but it's a cylinder. It's just crossing the shrinking sphere with Rn minus k, and you get a cylinder, and that also homothetically shrink to, in R3 we shrink to a line, or shrink to a copy of Rn minus k in a finite time. So I won't draw the evolution for cylinders, and these two are examples of self-shrinkers, meaning they shrink homothetically. They're homothetically shrinking solutions to the mean curvature flow. And self-shrinkers, as some of you might know, are singularity models, potential blow-ups for mean curvature, and they are of central importance, I guess, in the study of mean curvature flows. And one of the class that's particularly important to our discussion is the notion of graphical solution. So if your hypersurface can be written as a graph of some function from Rn to R, then the mean curvature flow equation reduces to the following parabolic PDE. So ut equals square root of 1 plus absolute nabla u squared times the divergence of nabla u over square root of 1 plus nabla u squared. And this is of our particular interest because if we know that the solution of mean curvature flow can be written as a graph, then you can use the standard parabolic PDE theory to try to tackle the problem. And for those of you who more keen to minimal surfaces, you would notice that the divergence nabla u over square root of 1 plus absolute nabla u squared equals 0 is the minimal surface equation. Okay. Now, the spheres and cylinders are like kind of the nice examples of mean curvature flows. In general, mean curvature flow can develop singularity in finite time. That's they don't disappear afterwards. Okay, so for example, the standard picture that you have here are these dumbbells. So it will be two spheres connected by a thin cylinder. So here, this radius R1 of the sphere is much bigger than the radius of the cylinder, which is R2. It's much bigger. And heuristically, because the spheres will shrink and the cylinder will shrink, you should see that this evolution of this dumbbell the sphere should shrink, and at some point the cylinder, because the radius is much smaller than the radius of the sphere, it will shrink to a line much sooner than the spheres. So this will create a singularity. So at these 2 points, there will be singularities, and these are genuine singularities. They cannot, that is an issue, and you cannot continue the usual notion of smooth flow past the singularity. So I guess one of the central object of study is how to extend these flows past the singularities. Okay, and just for the simple picture, you can imagine that if I in this picture, if I disregard this line of singularity, then I'm effectively just having two spheres, right? If I write this as if I can, this color kind of sucks. Yeah, well, we'll use this for this diagram anyways. So if you treat this as these two spheres, then you can run the flow. You can keep running the flow of these two spheres until they kind of disappears at the run points, right? And so this whole flow would be, away from the singularity. This whole flow would make sense, and that kind of explains to perhaps serves an example that you actually there might be a way to continue these flows past singularity in some sort of nice way. Okay, and one of the generalization of the mean curvature flow, for potentially singular happy surfaces is called the Brachy flow. It's a flow of varifolds. In this talk, I do not want to focus too much on the geometric measure theory side of these things. I'll give some definitions, and if you know, I guess that's good. But for our purposes, probably it's not super necessary to have all the geometric measure theory background. And for varifolds, I guess, if you're not familiar, you can think of it as a union of Lipschitz graphs, a countable union of Lipschitz graphs. Okay. And I do have the definition of Brachy flows here, so this is just some formalities. So you can see the Brachy flow is a flow of, in some sense, it's a flow of random measures. A varifold is a random measure in the Grassmannian bundle. So there are some technical assumptions. For example, it has to be the random measure has to be integral. First one, locally bounded first variation, and the generalized mean curvature vector H is orthogonal to the approximate tangent space. So I guess if you're a little bit more familiar with geometric measure theory, to define the mean curvature, you don't need. In general, you need a C2. You need a C2 to define the curvature, but in geometric measure theory, you can define the mean curvature just as the first. You can use the first variation of area to define the mean curvature, and that does not require any regularity. So I guess that serves as the basis of this definition. And some other assumptions, for example, you need the mean curvature to be locally L2, and then the last bullet point, which captures the mean curvature flow equation. And note importantly that you actually have a inequality here in the you actually have an inequality here in the definition, because you can show that this family is actually indeed a smooth mean curvature flow if and only if the equality holds. So I do need the inequality to make something more interesting flows of singular sets out of this. And indeed, bracket flow is a more general notion of mean curvature flow, and there are flows that cannot be described as mean curvature flow, but can be made sense of using bracket flows. Okay, so that's fine. And so one particular advantage is bracket flow allows us to make sense of singular initial state of mean curvature flow, so we can, so it allows us to speak about the evolution of cones in particular, which is singularity origin. Okay, but obviously it's a non-smooth type of flow, and it has some drawbacks. So the first drawback is that these flows may vanish abruptly, and that's something that I probably won't talk about. I'll just leave it here. That's due to the inequality of the equation, the third bullet point from before. And the second bullet point, the second point here is what we're going to focus on, because there could be multiple distinct bracket flows starting from a given non-smooth initial data, and in particular cones. And that's what we're interested in. Okay, so here is one potential class of flows that could come out of the cone. So given a smooth cone, so here by smoothness I mean that the cone is smooth away from the origin. A self-expander is asymptotic to the cone, is a hypersurface sigma, such that the mean curvature vector h sigma x satisfies this elliptic equation h sigma x equals x perp over 2. And the second condition is what means to be asymptotic to the cone here. So I meant that the limit as rho goes. So if you zoom in to the sigma, it kind of so at infinity it looks like the cone at infinity. And notice that obviously because the cone is singular, the origin the convergence can't be taken in C infinity log of the entire Euclidean space, so it has to be the entire Euclidean space minus 0. Okay, and the self-expander. Oh, sorry. One remark here is that in general you don't have to talk about self-expanders asymptotic to C to a cone. You can just say sigma is self-expander if it satisfies this elliptic equation, but and it is true that if you have an elliptic equation, this equation, a self-expander will be modular on the cone, so you will have a set theoretic limit. Given a self-expander, it will be a cone, but in general, even the variable convergence of the self-expander to the asymptotic cone is not known. You certainly cannot expect even more regular convergence. Now, in our cases, we are given a cone first, and then we find self-expander asymptotic to the given cone. So, in that case, because the cone is smooth, you can use your standard Schauer theory to deduce the regularity of the self-expander. Okay. So why is that? So I said that self-expanders are potential evolution of the cone. So that's because sigma is a self-expander if and only if square root t of sigma for t positive is a smooth mean curvature flow. Okay. So taking account of this asymptotic conical condition, you see that asymptotic conical self-expander corresponds to a potential evolution of the cone. Now, while the flow of the self-expander is smooth for t positive, you cannot say that it's a smooth mean curvature flow. It's a smooth mean curvature flow starting from the cone, right? Because the cone is singular while everything else is smooth. So you have to treat it as a bracket flow. Okay, so in the language of bracket flow, the cone C union with all these self-expander will be a bracket flow starting from the cone C. Okay, but it's not in terms of mean curvature flow. And here is our first theorem that's related to uniqueness. So if your cone is graphical, okay, so if your cone can be written as an entire graph over the hyperplane, then there's a unique self-expander asymptotic C. Okay, and that's a classical result of Eckert-Huisken, and to be honest, it has nothing to do with the cone structure. It's just the uniqueness of evolutions of Lipschitz graphs, the entire Lipschitz graphs. So that kind of covers a single cone case. Sorry, I should mention that. So in this definition, C intersect the unit sphere Sn is going to be called the link of the cone. And when I say a single cone, a double cone, I meant that the number of connected components of the link. So a single cone will have one connected component of the link. double cone will have two connected components of the links, and so on. Okay, so the single cone case is kind of very well studied, and there's not too much to say about that. But in general, there could be multiple distinct smooth self-expanders that's entitled to a given cone, and that's first demonstrated numerically by Angnant, Eilman, and Chop, and that's later on shown more rigorously using OD analysis by Hellman and Stauffer, and that exactly corresponds to the non-uniqueness that we mentioned earlier. And just to be clear, so what their examples are, so if you consider double cones, it looks like this. So if you consider double cone, actually let me use a different color as I promised. So if you consider double cone like this, let's go back. Here, double cone like this. That's rotationally symmetric. Well, it's ON across ON symmetric. So it's rotationally symmetric and it's reflection symmetric across some hyperplane. Okay. Then what Angnant and Eilman, Chop, and Hellman and Stauffer showed is that there are at least three self-expanders asymptotic as cone. Okay. So the first one. So if I get rid of this, so there will be a two-sheeted one. It looks like this. Yeah, but by the way, two-sheeted one always exists regardless of the cone angle. But for the one-sheeted one, you need the cone angle to be sufficiently large. Okay, so this two-sheeted one, the existence simply comes from this Eckert-Huesken result by treating a double cone as two single cones. So you can run the evolution for the two single cones and get the two-sheeted solution. So what they're able to show is that there's actually a one-sheeted guy. Okay, so the one-sheeted guy looks like it's catenoidal, so it looks like. Sorry, I shouldn't touch. So it looks like this. So there's one thin one-sheeted guy that looks like this, and there's like a fatter one-sheeted guy that looks like this. Okay, so that's if the cone angle is sufficiently large, the one-sheeted guy exists and it looks like this. Okay, so that's the non-uniqueness, and this I guess. If you're familiar with minimal surfaces, it should be compared to the case of minimal surfaces. So if you remember, for minimal surfaces, there was this problem of determining the minimal surfaces between a pair of parallel disks, or a pair of parallel circles. Okay, so if the distance between the two circles are sufficiently close, then you actually get three solutions, right? So there's the trivial solution, which is just a flat two disks. Right, and then there are two catenoidal solutions that looks like this, right? So there's a thin one which is unstable, and then there will be a fat one which is stable. Okay. So that's kind of a similar flavor result. Okay, so. That's on a short thing on the existence and non-uniqueness. So now let's talk about rotational symmetry. So if our given cone is rotationally symmetric, so we're interested in knowing how the symmetry of the cone affects the symmetry of the smooth self-expanders asymptotic to the given cone. Okay, so. For example, can we say that the self-expanders are rotationally symmetric? So that's so if you want to draw some analogy, then there was a classical result of Rick Shen that says that if you have minimal surface with two ends, then it must be a catenoid or all paraplanes. So that's kind of similar flavor because we have non-uniqueness. So, but first let's deal with a single cone. Okay, so if you have a single cone, then by the Eckert-Huesken result, you know that there exists a unique self-expander, and in addition, you can deduce that the self-expander is rotationally symmetric because in the rotationally symmetric case, you can reduce the the existence of self-expander to the solution of some certain ODE, okay, which is, if you just impose the symmetry, it's the same thing as the middle surface equation or something, and it reduces to this following ODE, and you can use existence uniqueness of the ODE to, well, not uniqueness because you have a boundary value problem, but you can use the existence theorem of ODEs to deduce that there is a rotational symmetric guy, but because the uniqueness holds, that means the unique evolution has to be rotationally symmetric. Okay, so that was so again the single cone case is kind of I already solved, so it's not super interesting. Okay, so here we're more interested in this double cone case. Okay, so when the link has two connected components, now we have to require in addition that they actually lie in different half spaces. So a cone like a so a cone that's it looks like this will not be allowed. So you have like a thin cone here, like a thin cone here with a fat cone outside and the same half space. So this is also, in some sense, this is also called a double cone because the link does have two connected components, but they are not allowed in our in our theorems are that because well, I also have no idea how a self-expander asymptotic this guy's gonna look like. So yeah, in general, more so we're requiring the cone to be of so this is no good, right? So we require a cone to be like the two connecting components lie on different half spaces. So because something like this, it doesn't have to have the extra O1 symmetry, so it could be like a thin cone on the top and the fat cone on the bottom. Doesn't matter. So this is okay, for example, and that's reflected by these forms. So by the explicit form of the cone. Okay. And some previous work on this rotational symmetry, and the first non-trivial result is obtained by von McGrath. In 2019, they proved that any mean convex, by which I meant the mean curvature is positive, self-expander asymptotic to the cone C, so here C is of the above form, is rotationally symmetric. And later on, this is generalized by Bernstein-Wen to any weakly stable self-expander asymptotic to C. Okay, so the time here is kind of messed up because the Bernstein-Wen paper is still at preprint, so I'm listening to archive time. So it actually came after von McGrath paper, and another thing is that any mean convex self-expander is in fact weakly stable. So the Bernstein-Wen result is a generalization. And then I should remark on their method. So their method is based on looking at rotationally symmetric Killing vector fields, and they show that the derivative along these vector fields are all zero, thereby deducing rotational symmetry. Sorry, my camera is kind of overlapping with the text, but you should be able to read that's components. And they are, especially the von McGrath methods, relies on this mean convexity assumption quite essentially. So using their method, that's the mean convex, the weakly stable or something is probably the best that you can get. So what we're able to show in 2021, there was a rather short argument, is that any smooth self-expander asymptotic C is rotationally symmetric. Okay, so this is based on a different method, which is everybody probably know it's a moving plane method that we'll be talking about in probably the second video. And so we show that any smooth self-expander asymptotic C is rotationally symmetric. Okay. Again, for which there could be a multiple of them. That's the point. And just a few remarks on this thing. So there do exist non-smooth self-expanders, and in particular ones with triple junction. So let me. So that looks like so that looks like it looks like catenoids on top, but draw a little better here. So triple junction is something that is three let's say in R3, it's three rays meeting at the equal angle of 120 degrees. Okay, so it looks like a canoid on top, but it's not. Let me just draw this. So it looks like this, basically. Okay. And on top, this will be rotationally symmetric. If you want, yeah, can't draw it very well. But here, basically, this is like 120 degree if you want. Okay, and again, the smooth guy would probably look like, asymptotically the same cone would look like this. Okay, and well, again, this construction is based on assuming rotational symmetry, and it's based on OD analysis. So so in fact, it will this triple junction will have like in R3 we'll have an S1 of triple junction on the hyper plane. Okay, and but yeah, these are like singular self-expanders, and so one of the, I guess, the more interesting, I mean, I'm gonna phrase this as like a very, very vague question. Okay, so it's an open question whether you have you also have a rotational symmetry of these singular self-expanders. Now, the part of the big issue with this question is the formulation, right? So triple junction is not necessarily the only singularity that can happen for a singular self-expander. There could be other there could be other type of singularities with like crazy high entropy if you want even. So it's kind of hard to formulate like what kind of self-expanders you're thinking, like what class of self-expanders you're looking at. So there's some big issue with formulations. I suspect in this case, because this case we constructed is also rotationally symmetric. It's just our method cannot show it. I suspect that in our case, if you have a self-expander that's smooth away from a given hyperplane, and only has triple junction, and only has a triple junction singularities, and the asymptotic cone is ON cross O1 symmetric, then you should probably have rotational symmetry as well. But you would require some sort of singular Hopf lemma to deduce that, I believe. And I thought about this for a little bit. I think that the method is like, the statement is kind of awfully specific, so I didn't think it was that good of a result, anyways. So it's I ditched it basically. Anyways, and so that was one direction. Now the other interesting question is what happens if the cone has if the link of the cone has more than 3 components, so like a triple cone or something. So a standard example here would be, so you take a double cone, and you take the union with a hyperplane. Which, if I can draw it very well, I cannot draw it very well. But you take a union with a hyperplane, basically. Okay. So that would be a rotationally symmetric triple cone, and that would be another natural question to ask: what happens if you have 3 or more connecting components, and it is not expected that the rotational symmetry continues to hold. So in fact, you can probably find the self-expander that asymptotic to this cone that is not rotationally symmetric. So for this, if you want to draw an analogy, if you know the Costa surface, the minimal surface, it has 2 catenoidal ends and 1 planar end, but it's not rotationally symmetric. It only has a D4 symmetry, I believe. I think D4 symmetry, but I might be wrong on that. But the point is that it doesn't have a rotational symmetry, and that you can probably produce by there are also higher genus examples that you can produce by desingularizing the plane and the catenoid. So you do expect something similar to happen here in the self-expander case. So so you can imagine desingularizing the catenoidal self-expander asymptotic to the rotationally symmetric double cone and the hyperplane. to produce something that's asymptotic to the triple cone and only has a, I guess, dihedral symmetry or maybe platonic symmetry. Either way, I'm not too sure on the actual symmetry group, but it is not expected that the general rotational symmetry continues to hold for if the cone has three or more, at the link of the cone has three or more connected components. Okay, so that is our that is the smooth part, and that is the smooth part of the theorem statement of our result. And I guess in next video, as I said, I will be talking about the generalization to potential singular evolutions starting from the cone.